this video, we're going to talk about the types of symmetries the graphs of a function can have. There are three basic ones you need to be aware of: even symmetry, odd symmetry, or neither. We call functions even if they're symmetric with respect to the y-axis, if the y-axis is a line of symmetry that goes down the middle and splits the shape into two mirror images. We say a function has odd symmetry if it's symmetric with respect to the origin. This means that if you turn it 180 degrees, it should look the same upside down as it does right side up. A function that is neither, it won't be symmetric across the y-axis, and it won't be symmetric with respect to the origin either. Notice where this graph has its y-intercept at +3. If I spin the graph upside down, is the y-intercept still at +3? No. Therefore, it is not symmetric with respect to the origin, and we say that it is neither. When you have the graph of the function, it's pretty easy to sort out what type of symmetry it has. It's a little bit trickier if all you have is the equation for the function. This slide summarizes the information you need to know. One of the key takeaways here is that in each case, you need to replace x with negative x in the original function. Then you look at what happens to the function as a result. If the function has even symmetry, the right side of the equation will stay the same. If it's an odd function, every term on the right side of the equation will change sign. If it's neither, the right side of the equation will change, but not every term on the right changes its sign. Above these descriptions are the shaded boxes, which say the exact same thing, just in mathematical notation. Let's get to some examples. So here's an example like I was just talking about. Determine whether the function is even, odd, or neither. Then determine whether the function's graph is symmetric with respect to the y-axis, the origin, or neither. To determine if a function is even, odd, or neither, the technique that we use is to replace the x in the function with a negative x. You always begin that way. So I am going to draw a rectangle apparently, which is not what I wanted to do. I will begin by plugging in negative x. I do that everywhere I see an x. And notice I use parentheses just to be very careful so I don't lose that negative sign. Now you simplify the right-hand side of the equation. If I have a negative number and I raise it to the fourth power, such as -2, -2 times -2 times -2 times -2 becomes positive. So a negative x to the fourth power is really the same as just x to the fourth power. A negative x to the sixth power, anytime that exponent is even, the result will be positive. So it'll be the same as positive x to the sixth. And then I bring down my +3. Now at this stage, I go back and compare this to the right-hand side of my original. If they are the same, which they are in this case, this is equal to f of x, that always means the function is even. And if the function is even, we learned that it will always have y-axis symmetry. Okay, now let's try another example and suppose that I have an odd exponent in there. Let's see what happens then. I'm going to define my second function to be g of x equals 3x cubed minus 4x. I begin with the same technique. I always replace the x with a negative x all the way through the right-hand side. In this case, when you have an odd power, if you raise a negative number, like -2, to an odd power, it will always turn out to be negative. So therefore, this first term, 3 times -x cubed, is going to end up being negative. And here's how I represent that. In the second part, a -4 times a -x will become positive. So I have a positive 4x. Now it's time to compare again. I compare the right-hand side to the original right-hand side. Are they the same? No. So the next thing I look for is to see if they're exactly opposite signs. 3x cubed is now negative 3x cubed. Negative 4x is now positive 4x. If every term on the right-hand side changes sign, ends up negated, is how we write that in symbols, that means your function is odd. And of course, the last situation that could possibly happen is when you have a function and you don't have either of those things happen. So let's take an example of 4x squared minus 2x. I will begin again, substituting negative x. A negative x to an even power becomes positive, so this term will be the same as just 4x squared. A negative x times a negative 2 becomes positive. Now I compare. I compare the right-hand side to the original right-hand side. Are they the same? No, so this function's not even. Have all of the terms had their signs changed? Well, it's true in the case of negative 2x and positive 2x, but it's not true for the first term. So if the right-hand side changes, but it's not just a simple case of all the signs changing, this is when we say that h of negative x was not the same as the original function, and h of negative x was not the same as the terms changing their signs. Therefore, because of both of these facts, this is when we say the function is neither even or odd. We're going to end on an easier note. This problem says using the graph of the function, determine whether this is even, odd, or neither. So once again, you have to know what type of symmetry this function is supposed to have. If it's even, it should be symmetric along the y-axis, right here. Now it might look like it is, but make sure you look at this graph closely, because I have a point here that is just 1 unit away from the y-axis. On the other side, the first point is 2 units away. So this does not have y-axis symmetry. The two sides need to be exactly mirror images of each other. In this case, I would need to have my point located here and have a graph that looked like that, but I don't. So this graph does not have y-axis symmetry. Okay, what about the symmetry with respect to the origin? Remember, the idea there is that you always rotate the graph around the origin, this point here, and if you spin the graph upside down, or equivalently, if you kind of turn your head upside down and look at the graph, what you'll notice is right now the graph has a y-intercept of 1. If I look at the graph upside down, it looks like the y-intercept is negative 1. There is no longer a y-intercept at 1. For this reason, this graph does not have odd symmetry, and therefore, this has to be a case of neither. That's all you need to know about features of graphs.